Good day everyone, I am Junalyn A. Gongora and for today's video, we're going to discuss the Scheffé test in analysis of variance. So what is Scheffé test? The Scheffé test, also called Scheffé's procedure or Scheffé's method, is a post hoc test used in analysis of variance. It is named for the American statistician Henry Scheffé. After you have run ANOVA and got a significant F statistic and you rejected the null hypothesis that means are the same, then you run Scheffé test to find out which pairs of means are significant. The Scheffé test corrects alpha for simple and complex mean comparisons. Complex mean comparisons involve comparing more than one pair of means simultaneously. Out of the three main comparisons tests you can run, the other two are Fisher's LSD and Tukey's HSD. The Scheffé test is the most flexible, but it is also the test with the lowest statistical power. Deciding which test to run largely depends on what comparisons you're interested in. If you only want to make pairwise comparisons, run the Tukey procedure because it will have a narrower confidential interval. If you want to compare all possible simple and complex pairs of means, run the Scheffé test as it will have a narrower and confidence interval. Calculating the test. Only run this test if you have rejected the null hypothesis in an ANOVA test, indicating that the means are not the same, otherwise the means are equal, and so there is no point in running this test. The null hypothesis for the test is that all means are the same. The alternative hypothesis is that means are not the same. This test is usually calculated with software. Like most statistical tests, you find a critical value and then compare it with the test statistic. Reject the null hypothesis is the Scheffé test. Statistic is greater than critical value. Example number 1. A clinical trial is run to compare weight loss programs and participants are randomly assigned to one of the comparison programs and are counseled on the details of the assigned program. Participants follow the assigned program for 8 weeks. The outcome of interest is weight loss, defined as the difference in weight measured at the start of the study, baseline, and weight measured at the end of the study, 8 weeks measured in pounds. Three popular weight loss programs are considered. The first is a low-calorie diet, the second is a low-fat diet, and the third is a low-carbohydrate diet. For comparison purposes, a fourth group is considered as a control group. Participants in the fourth group are told that they are participating in a study of healthy behaviors with weight loss only, one component of interest. The control group is included here to assess the placebo effect, weight loss due to simply participating in the study. A total of 20 patients agree to participate in the study and are randomly assigned to one of the 4 diet groups. Weights are measured at baseline and patients are counseled on the proper implementation of the assigned diet with the exception of the control group. After 8 weeks, each patient's weight is again measured and the difference in weights is computed by subtracting the 8 weeks weight from the baseline weight. Positive differences indicate weight losses and negative differences indicate weight gains. For interpretation purposes, we refer to the differences in weights as weight losses and the observed weight are shown below. Is there a statistically significant difference in the mean weight loss among the 4 diets? We will run the ANOVA using the 5-step approach. Step 1. Set up the hypothesis and determine the level of significance. Step 2. Select the appropriate test statistic. The test statistic is the F statistic for ANOVA. Step 3. Find the critical value. And Step 4. Compute the test statistic. Okay, so para mas mapadali at makompute na natin agad ang ating ANOVA and malaman na natin kung ire-reject ba natin yung null hypothesis is gumamit tayo ng Excel. So, first, pumunta tayo sa Excel, then copy the given data. Then, paste sa ating Excel. Sa Data tab, then hanapin natin yung Data Analysis. Then, click the ANOVA single factor. Then, okay. Then, i-click natin yung mga cells kung saan nasan yung data. Okay, so i-highlight natin siya. And then, yun. So, yan na yung result. Using the F table, we're going to find the F critical values. So, our F critical values is 3.24. Then, let's graph our F critical values is 3.24 and our F value is 8.56. Therefore, we're going to reject the null hypothesis. After rejecting the null hypothesis, we're going to use the Scheffé test to identify which entry or which factor rejects the null hypothesis. Before proceeding to perform the Scheffé test, let us first identify the respective pair that are being compared. So we have low calorie and low fat, low carbohydrate and control group. Next pair, we have low calorie versus low fat, low calorie versus low carbohydrate, low calorie versus control, and low fat versus low carbohydrate, and low fat versus control group, and we have low carbohydrate versus control group. So let's start performing the Scheffé test. For our first pair, we have low calorie and low fat. For the formula for the critical value, so we have K minus 1 times F alpha or K minus 1 times the critical value. So we have 4 minus 1 times 3.24 is equal to 3 times 3.24 is equal to 9.72. For our F value using the Scheffé test formula, we have min of 1 minus min of 2 raised to 2 all over sum of squares within times 1 over total number of group 1 plus 1 over total number of group 2. So we have 6.6 minus 3 raised to 2 all over 2.95 times 1 over 5 plus 1 over 5 is equal to 10.98. Since our F value for low calorie and low fat is 10.98 and it falls in a critical region, therefore low calorie and low fat are significant in our problem. For pair number 2, so we have low calorie and carbohydrate. So our F critical value is 9.72 and our F value using the Scheffé test formula is equal to 8.68, and 8.68 does not fall in our critical region. Therefore, low calorie and carbohydrate is not significant in our problem. For our pair number 3, so we have low calorie and control group. So our F critical is equal to 9.72, and our F value using the Scheffé test is equal to 24.71. Since 24.71 falls on the critical region, therefore low calorie and control group are significant. For our third pair, we have low carbohydrate and low fat. For our F critical value, we have 9.72, and for our F value using the Scheffé test, we have 0.14, and since 0.14 does not fall in our critical region, therefore low carbohydrate and low fat is not significant in our problem. For our next pair, we have low fat and control group. So once again, our F critical value is equal to 9.72, and our F value using the Scheffé test is equal to 2.75. Since 2.75 does not fall in a critical region, therefore low fat and control group is not significant in our problem. Our next pair is low carbohydrate and control group. So our F critical value is equal to 9.72, and our F value using the Scheffé test is equal to 4.10, and since 4.10 does not fall in our critical region, therefore low carbohydrate and control group is not significant in our problem. To wrap up our computation, so we have two pairs of variables that are significant in our problems. So these are low calorie versus low fat and low calorie versus control group. So since the F-test value for low calorie versus low fat and low calorie versus control group is greater than critical value 9.72, the only significant differences are between low calorie and low fat and low calorie and control group. For our example number 2, so we have the number of grams of fiber per serving for a random sample of 3 different kinds of food is listed. Is there sufficient evidence at 0.05 level of significance to conclude that there is a difference in mean fiber content among breakfast cereals, fruits, and vegetables? So using the Microsoft Excel, it's easy for us to compute the ANOVA for this sample. Using the F table, our critical value is equal to 3.47. Since our critical value is equal to 3.47 and our F statistic value is equal to 2.13, and 2.13 does not fall in the critical region, therefore we do not reject the null hypothesis. So since we do not reject the null hypothesis, we will not perform the Scheffé test. For our example number 3, we have the employees at toll road interchanges. A state employee wishes to see if there is a significant difference in the number of employees at the interchanges of 3 state toll roads. The data are shown at 0.05 level of significance. Can it be concluded that there is a significant difference in the average number of employees at each interchange? Using the Microsoft Excel, we're going to compute the ANOVA for this problem. After computing the ANOVA for this problem, we're going to graph. So our critical value for this problem is equal to 3.68, and our F value from the ANOVA test is equal to 5.04. Therefore, we reject the null hypothesis. Using the Scheffé test, we're going to identify if there is a significant difference between the three pairs from this problem. So our first pair is Pennsylvania Turnpike and Greensburg Bypass. For this pair, our F critical value is equal to 7.36, and using the Scheffé test formula, our F value is equal to 8.72. Since 8.72 falls on the critical region, therefore this pair has a significant difference. Our next pair is Pennsylvania Turnpike and Beaver Valley Expressway. So our F critical value for this pair is 7.36, and the F value using the Scheffé test is equal to 6.21, and 6.21 does not fall in our critical region, therefore this pair has no significant difference in this problem. For next pair, we have Greensburg Bypass and Beaver Valley Expressway. So our F critical value is equal to 7.36, and our F value using the Scheffé test is 0.21. And since 0.21 does not fall in our critical region, therefore this pair has no significant difference in this problem. So for the conclusion, since the F-test value for Pennsylvania Turnpike versus Greensburg Bypass is greater than critical value 7.36, the only significant difference is between Pennsylvania Turnpike and Greensburg Bypass. So that is all my report. Thank you for listening.